All right, let's dive in. The next great leap in technology, in computing, in sensing, in communications, it's not just going to be written in code. It's going to be built, atom by atom, out of brand new kinds of matter. Today, we're taking a look at the wild and powerful world of quantum materials, the physical foundation for our entire quantum future.
So, what is going to power this new age? If you're thinking silicon or maybe even AI, you're only seeing part of the picture. The real engine of progress is something way more fundamental and, honestly, a whole lot weirder.
So here's our game plan. First, we're going to get a handle on what this second quantum revolution actually is. Then we'll dig into the single biggest roadblock holding it back, the materials. We'll see how that creates a huge performance gap for things like quantum computers, and then walk through the global roadmap designed to fix it, all leading up to the ultimate goal of this whole mission.
Okay, so to really understand where we're going, we've got to take a quick look back at where we've been. See, we're all living in a world that was built by the first quantum revolution. That first revolution, it gave us the science for lasers, for transistors, basically for everything in your smartphone. The second quantum revolution, which is happening right now, is a whole different ballgame. It's about going from just observing these weird quantum effects to actually controlling them. Think of it like going from just watching lightning strike to actually harnessing electricity. And that control unlocks tech that sounds like science fiction. Quantum computers, sensors that can detect things with unbelievable precision, and communication networks that are fundamentally unhackable. But, and this is a huge but, all of those incredible technologies, they absolutely depend on us being able to invent and manufacture totally new types of materials. Without the right stuff to build with, the quantum future just stays on the drawing board. And that brings us to the stars of the show today, quantum materials. We're talking about things like superconductors, which can carry electricity with literally zero energy loss, or 2D materials, like graphene, a sheet of carbon that's only one atom thick but stronger than steel. It's really no wonder that our sources say these materials are getting unprecedented attention. They are the key to making all this quantum tech work reliably.
And this Venn diagram just illustrates the challenge perfectly. See, right there in the middle, you have these shared problems that plague everybody. Things like qubit coherence, which is basically how long can you keep a quantum bit in its fragile state before the outside world messes it up. And the fact that a lot of this stuff only works at super cold temperatures. The beautiful thing is, if you solve the material problem for one of these fields, you end up helping all of them.
All right, now let's zoom in on the big one, the main event, building a large-scale, useful quantum computer. This is where those material science hurdles create a just massive performance gap.
So, one of the biggest bottlenecks is a process called quantum transduction. The best way to think about it is like this. Different parts of a quantum computer speak different languages. A superconducting qubit might talk in microwaves, but to send that information anywhere, you need to turn it into light. Quantum transduction is supposed to be that universal translator. And right now, our translators are not very...
And this chart, wow, this just lays the problem bare. It maps out all the important metrics for a good quantum translator. That little blue shape in the middle, that's us. That's our performance today. That big orange shape on the outside, that's where we need to be. And the gap between them, well, you can see it. It is enormous.
And let's put some real numbers on that gap. Just look at the first line, transduction efficiency. Right now, it's around 10 to the minus 6. What that means is, for every million quantum signals you try to translate, only one gets through correctly. Just one. The 10-year goal is to get that number close to 1, so nearly perfect translation. That is a monumental leap, and solving it is purely a material science problem.
So when you're staring down a challenge this huge, you can't just cross your fingers and hope for a lucky break. You need a plan. And that is exactly what the research community has put together, a detailed strategic roadmap to guide innovation and start closing these performance gaps.
And just to be clear, this isn't some academic wish list collecting dust on a shelf. As the source material says, this roadmap is designed to guide investment. It's there to help governments and companies answer that critical question, okay, what do we fund right now to actually make progress?
And the whole approach is incredibly systematic. It breaks this massive problem down into bite-sized pieces. First, you identify the main challenges, like our translation problem. Then, you define what good actually looks like. Those are the figures of merit. You set realistic targets for the next few years. And finally, you figure out the key enablers, everything you need to make it all happen.
So let's look at those enablers, because this part is fascinating. The first one is all about people. The roadmap calls for a whole new generation of what they call quantum smart researchers.
That means getting new people into the field, training specialized technicians who can actually run all this complex equipment, and creating university programs that mix physics, engineering, and material science together from day one.
The next enabler is policy. You know, innovation like this doesn't happen in a vacuum. It needs a coordinated national plan. It needs international partnerships so you can work with the best minds and facilities around the world. And it needs smart economic policies, like tax incentives, to help a local quantum industry actually get off the ground and build a reliable supply chain.
And finally, you need the gear, the really, really expensive gear. This means huge investments in infrastructure. We're talking about shared nanofabrication facilities, pilot production lines to test things at scale, and access to these incredibly advanced tools that let you analyze new materials literally at the atomic level.
Okay, so we've got the plan, we've got the enablers lined up, but where is all of this actually heading? What does success for this materials roadmap even look like? What's the end game?
It looks like this. 1 million. That's the number. Over 1 million high-quality, stable, interconnected qubits. That's pretty much the accepted target for building what's called a fault-tolerant quantum computer, a machine that can correct its own mistakes and solve really world-changing problems.
And the key point here is that this isn't just about building a bigger, faster calculator. A 1 million qubit machine is a turning point for humanity's problem-solving ability. It's the kind of system that could design new medicines from scratch, discover new materials like a room-temperature superconductor, untangle global climate models, solve problems that are literally impossible for any supercomputer we have today.
Which really brings us to the final thought. A machine with that kind of power could fundamentally change our world. The roadmap we've just talked about is the step-by-step, material-by-material plan to build it, and it leaves us with maybe the most important question of all. Once we actually have it, what problem should we ask it to solve first?